Hello, let's start today's session, that is week 4 videos, interactive live session on week 4 videos. So let me go through the recap of week 4 videos. First one is 2D convolution. So 2D convolution introduction was done in the last week, week 3, and after that 2D convolution and equations and the concept of doubly circular and block matrices are explained in week 4. Then we have different blur models. So mainly two types of blur models are explained. First one is pillbox model and the second one is Gaussian blur model. And the third topic was space invariant blur and about space variant blur also. Then we have shape from X. So X stands for stereo, shape from focus, shape from shading, and shape from photometric stereo. So these all are the topics in week 4. So first we will go to 2D convolution part. Okay, so in 2D convolution, unlike the case of 1D convolution, we have a 2D input here, f of mn, and it will be passed through a system h of mn to get an output g of mn, where h of mn is the lens impulse response. So can be considered as a light is passed through a lens and some output will be given at the image plane, g of mn. And we have already proved that lens is a linear space invariant system, so we can use convolution to get the output, convolution of input and impulse response. And so as an example in the lectures, it was given that h of mn lies here only, other values are 0. So this is 0 0, so this point is 0 0, this point is 0 1, 1 0 and 1 1. Other points we have 0 values. So sir explained how to get circular convolution, how to get linear convolution answer by using circular convolution, and he wrote the equations here, and at last a matrix is formed. So an equation like G is a vector is equal to H and F is a vector. So it is derived, and H can be written as a doubly block circular matrix. So what is that? So here we can see that the whole structure of this matrix itself is a circular structure, because the first block here repeats in the second row here, and it is repeated at the third row here, and inside a particular block that is a circulant also. So the whole matrix has a circulant structure here, and each of the blocks has and the whole circulant matrix and the whole matrix H has a circulant structure, and each of the sub matrices have a circular structure. So here you can see h0 0 0 h0 1, then a circularly shifted version h0 1 h0 0 0 0 h0 1 h0 0. So we can get an h like this, then we can just multiply that with the vectorized form of the input image to get the output. So as an example, question 1 is find the output of an LTA system if the input x is given. So f is given here. So here f is given and h is given. So you have to find out g. So g vector
will be like what? Circular matrix. H00 is 1, right? So 1, 0, 2. Then the circular version. 2, 1, 0, 0, 2, 1. Then here 0, 0, 0, 0, 0, 0, 0, 0, 0. And the upper column, upper row. 1, 0, 1, 1, 1, 0, 0, 1, 1. Then the circularly shifted version of the first row. So you'll get 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 2, 2, 1, 0, 0, 2, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Then circularly shifted version of this row. 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 2, 2, 1, 0, 0, 2, 1 into F. F structure is like F01, F02, F01, F02, F0, F0, F02, so sorry, F00, F01, F02, F10, F11, F12, then 0, 0, 0. So the answer becomes 1 plus, okay, 0, 1, then 2 plus 2, 4, then 4 plus 0, 4, then 4 plus 0, 4, then 1 plus 0, 1, wait, 1 plus, okay, 1 plus 3 plus 8. 12, right, 1, okay, then 1 plus 2, 3 plus 3, 6, so wait, okay, so you can calculate like this, then you will get what the output of the system. Then you can just write it as a matrix. Okay, F00, G00 here, G01, G10, and G11 to get the output matrix. So this is about a 2D convolution. So 2D convolution can be written as the product of the row vector, column vector corresponding to the input image and the impulse response corresponding to the system. But the impulse response can be written as a doubly block circular matrix. Then only we can write it as a matrix multiplication. Then the topic is blur models. So the first blur model is pillbox model. So here we have the same value for all the x and y. So h of xy is the h of xy is the impulse response of the lens. Then that can be written as 1 by pi r b square. So here RB is the blur radius. So that's a constant value, right? So that depends on only R0, U0, working distance and the depth. So for every depth value, RB will be same. Then so the whole equation will be the same for all x and y. No. So it will be looking like a circle and there will be values in all the locations. Then the next blur model is Gaussian blur model. In Gaussian blur model, that depends on every x and y. So it will be a bell structure like this, and at the center, the value will be high. H will be high, and along as we go along the side, it will be reduced. So that is Gaussian blur model. So question 2 is identify the blur kernel corresponding to pillbox blur model and Gaussian blur model. So which is the pillbox model and which is the Gaussian blur. So can you tell which one is pillbox blur model? So the first one is the pillbox blur model, and the second one is Gaussian blur. Okay, and we know that this is the width and height of the image, and this is the amplitude of the blur. Okay, so it means that at every pixel the Gaussian kernel value is different, so it affects the pixel individually in every pixel. Okay, and the next question, it also relates to Gaussian filter plots. Match the filter specification with the Gaussian filter plots. So here three specifications are given like this: A, B, and C. So we have to match every specification with the filter plot. Okay, so can you tell which specification matches with the given plots? Okay, so it is written in a very small form. So I'll give that. So I'll write it again. So filter size is 50. Filter size is 50. Then sigma is equal to 9. Sigma equal to 7. Then filter size is 50. Sigma equal to 11. Filter size is 50. Sigma equal to 2. So that is what they have written. So we have to find out. So here in the image you can see that the filter size is 50. No, here the filter size is 50 only. So at the bottom you can see that the filter size is 50. Okay, 50. It's a square like structure, and the amplitude has a sudden decrease here, but in the third image the decrease is very slow. Okay, so the third picture has sigma, what, a lower sigma or a higher sigma. Standard deviation means variation from the mean. So if it is very less, means the variation from the mean is less. Or the sigma can be considered as like this now. So we can say that the third picture has more sigma. So we can match it like this, here, here, and okay. So the more the flat the Gaussian kernel, more will be sigma. Next is about space invariant blur. So in space invariant blur, as the name indicates, it is space invariant. The blur is independent of the space. So at every position, the blur will be the same. It won't depend on space. So that is meant by space invariant blur. If you have a defocus blur, then if you are focusing, if you are capturing a picture of a planar scene, then there will not be any space depth difference now. And if the focus of the lens is bad, then only we'll get a blur. There will not be any blur corresponding to depth, but there will be a blur corresponding to the defocus blur. So the error in the focus of lens. So that type of blur is known as space invariant blur. As you can see here, every position in the image is equally blurred. No. So this type of blur is known as space invariant blur. Blur is independent of the space. Then comes space variant blur. So here in this picture, you can see that it is a space variant blur. So blur depends on space. At every space, blur is different. So here blur is low, no, but at the back side, blur is very high. So blur depends on space. That means it's a space variant blur. According to space, blur will be varied. So one question 4. Identify type of blur in the following images. So you have to tell which one is space invariant and which all are space variant blur. So the first one, you can see that space is different at different position. Here it is small and here it is very less. So you can say that it is a space variant blur. The next one, we can't see any difference in the blur inside the image, so it is a space invariant blur. And the third one has more blur at the back side and no blur at the front side. No, so it is also a space variant blur. And one question. So this topic is actually like the previous topic only, week 3 videos about blur radius. So the question is, consider a camera setting with aperture size 8 millimeter and focal length 30 millimeter. Working distance of the camera is also given. Lens sensor separation is given. Plane scene is placed at 100 millimeter and the resolution is given. Width of the sensor plane is given. Then the question is, how many pixels will be a given blur radius occupied? So we know the blur radius equation, that is RD is equal to R0 U0 into 1 by omega d minus 1 by capital D. So where R0 is aperture size, no, aperture radius. So this is given here, 8 millimeter. Then U0 is what? Whether it is focal length or working distance. Oh, okay. Let me write working distance is here 1. So here working distance is 120 mm. Then that is given in the question. So 120 mm is there. Then the depth D is given here. A plane scene is placed at 100 mm. So D is given as 100 mm. Then so focal length is given 30 mm, but that is not being used in the equation. No. Then U0 is what? Lens sensor separation, that is 40 mm. So you'll have to find out RD, blur radius, in millimeter. So you have to multiply like this, 8 into 40 divided by so 1 by 120 minus 1 by 100. You will get so you'll get around 0.533 into 10 raised to minus 3 millimeter. Okay, and it is given that the sensor width is 10 millimeter and the sensor width is 10 millimeter. So 1280 pixels. So a sensor is having 1280 pixels in the width dimension. No? So 1280 pixels will have 10 millimeter. So we have to convert this RD into pixels. So this 0.533 into 10 raised to minus 3 millimeter becomes how many pixels? 1280 divided by 10 into this value, 0.533 into 10 raised to minus 3. So you'll get around 68 point something. So the answer will be what, 69 pixels. So it is a problem regarding blur radius. So the topic was already covered in the last lectures. So it's a standard question to find out the blur radius when aperture radius, object distance, working distance, and depth is given. Okay, so this is question 5. So those who come late, so I explained about okay, I explained about 2D convolution. So its equation is already given in the uh, lectures. So I have given one question, that is question 1, to find the output for a particular input, and the impulse response is also given. So you have to convert that impulse response. You have to convert that impulse response to a block circular matrix. So if you are converting that H to a block circular matrix, then you can just give the output of the system G as a multiplication of this H and F, where G and F are a column vector representation of the input image and the output image. Okay. So after finding this multiplication output, you just arrange this G as a matrix. That's all. Then you will get the final output. Okay. Then I explained blur models, pillbox model, Gaussian blur model. Then we have okay, one question regarding which type of blur kernel. First one is pillbox model, second one is Gaussian. Then we have one question regarding standard deviation. So the question was, which one has more standard deviation, sigma. So the answer will be more flat as the plot, more will be the sigma. Okay, so the third picture will have maximum sigma, sigma equal to 11. First one has lesser sigma, sigma equal to 2. Then space invariant blur. So at every pixel positions, blur will be the same. That type of blur is space invariant blur. Then comes space variant blur. In space variant blur, we'll have blur at different position. Different blur will be at different position. That is not a space variant blur. Space depends on blur. Sorry, blur depends on space. So this question is to identify type of blur in the following pictures. First one is space variant. Second one is space invariant, because in the whole image we can see a similar blur. But if you are seeing different blurs at different positions of the image, it is space variant. Then question 5 is about what I explained about blur radius. Then shape from X topics. So X first we'll discuss X shape from stereo. Shape from stereo. So in the stereo setup, one camera will be here and will take picture of a 3D world. Okay, so this is the 3D world. First picture will take like this at this position. Then we'll just shift that camera to another position. Then we again, so the world will be at the same position, no, this position itself, but we are capturing from here. Okay, so we'll get another image like this. So we'll have two images, left image and right image. So from left and right image, you'll find what depth of the sea. So that is what we are doing in stereo. And in the lectures, it is derived that what that Z is a depth. So the depth will be focal length into B divided by disparity. So what is B? So how much we shifted the camera, that is the value of B. Okay, that we know, right? So while we're capturing the images, we know what's the value of B. So we know B, and if we know F, and if you know disparity. Disparity is what? The distance between the same points in both the images. So that is disparity. So say here, this is the first image and this is the second image. If the point is here, one point is here, point A, then another point is here, point B. Not another point, the same 3D point, but in the second image. That is B here. Then, so we know A is here. A is at a position of 10, 10. Then at the second image, we know that A is here. So the distance between this and this is known as disparity. So if we know the camera movement, how much we move the camera B, small b, and if we know the disparity, then we can get the depth of that point. Okay, that point corresponding to point A and B. So same 3D point is mapped to point A and B. No, so if we know disparity, focal length, and base length, then we'll get this. So the next question is about stereo images. For capturing stereo images, a planar scene situated at the depth of 3 meter, camera with a focal length 0.05 is moved by a distance of 0.1 meter. What would be the disparity in the image? So depth is given, but we have to find the disparity. So the equation is depth is equal to FB disparity. So disparity will be what? F into B by D. That is equal to 0.05 into zero point 0.1 by 3 to get 0.0016 inches. Okay, so that we can convert it to pixels if the pixel resolution is given. Okay, so this is about stereo. Then next axis. So the next axis shape from shading. So in the lectures it is already explained that uh, in shape from shading, the structure of the object will be found out from by using the light and the what the surface normal of the object. So that is explained in the lectures. Then photometric stereo, if you have an object, then the source light is placed at different position, then we are capturing different images like this. Then from that a single shape will be extracted. So that is known as photometric stereo. That is already explained in the lectures. Then we have shape from focus. Shape from focus, that is an important topic, and it is also an interesting topic. Here we have a simple 3D structure as a coin or something. Okay, so on the coin we will have some small structure. No, so that will be bulging from the surface of the coin. Then if we arrange a microcentric setup like this, then if you are capturing, this is the lens. Okay, so this is a microcentric structure. Then if we move this coin upwards, delta d. Okay, so first we'll capture the image of the coin at this depth, then we'll shift that coin to a delta d distance. So the coin will be here, then we'll capture one image. Next it will be shifted to delta d again, and the point will be here. So at each time we'll get one image like this, then a red image like this, then a green image like this, right? So we'll have a number of images like this. So from those number of images, we'll find the 3D structure of the coin. That is the aim. So it is shape from focus. At different focal distances, we'll place the object to get different images, and from the different images, we'll find the shape of the image. So how will we find? So if we have a stack of frames like this, we'll take one pixel like this, one pixel. Okay, so I'll draw like this. So this is a stack of frames, and take a one pixel here. Okay, then just watch the values along that pixel at every frame. Okay, so uh, so in one of the frames, the focus value, the focus measure will be very high. So uh, so that 3D point is focused at any of the planes. So the focus measure of that point at different planes will be different. In we may say that in the 10th frame it is focused more. So we have to find out the focus measure of that point at every frame. So that is given in this picture. Okay. So the first point will draw the focus measure. Second frame will draw the focus measure. Third point will draw the focus measure. This single graph is for one single pixel. Okay. Then we'll find the maximum focus point. Okay, so the plane at which we have the maximum focus value. So for we can find focus value by using focus operators. Okay, so that will be discussed in the next lectures. So by using these information, we'll find the depth at every pixel location. That is our aim. Okay, so this is about space shape from focus. So the question 7 is about shape from focus. For the experiment of the shape from focus, an optimum choice of platform size delta D is. So platform step size delta D means how much we are shifting the platform to get different images. So what would be the answer? Answer A, B. A is f by 10, focal length by 10. B is depth of field. C is working distance. So if you are shifting an image by delta D, we should get a different focus measure at every point. No. So what is depth of field? Depth of field is at a 3D world, some of the portions will have same focus value. So that is known as depth of field. So that step size should be greater than depth of field. No. So because if we are taking inside the depth of field itself, we'll get the same focus measure at some of the points. So that is not required. We should get another focus value if we are shifting delta D. So delta D should be depth of field. So that doesn't depend on working distance or vector. So the answer is B, depth of field. So then we have lab assignment, about lab assignment 4. So the question is, so this lab assignment is comparatively very easy than the first 3 assignments. So we have an image like this, a manual image like this. Okay, we have to blur it. That's all. So using space invariant blur. Space invariant blur means at every position a blur will be the same. So at every position we have to do the convolution. So we have to do the 2D convolution. 2D convolution is explained, no? So for doing 2D convolution, we have to use some blur kernel. Okay, so we have image like this. We will have a kernel like this. Kernel will be of small size, no? So this kernel should be placed on top of the image first. So like this, and we'll have to do the sum of product of all the corresponding values. Okay, then we'll get one value that will be saved to 1 pixel. Then this kernel should be shifted. So convolution is what? Shifting, multiplication and addition operation. No, so it is shifted to right. Then you will find one value, and that pixel is again saved to the next pixel. Like that, you will shift to at the end of the image. No, then you will get last value. So you will get a convolution output like this. So that will be your blurred image. That is what you have to do. So for this you have to use some Gaussian kernel. No, so Gaussian kernel can be defined in Python. So there is already one function written in the assignment. So there we have to pass one sigma value and size. So sigma value I explained, like uh, more flatter the plot, more will be sigma. So sigma value, some sigma values are already given in the question, so you have to take one sigma. So say sigma equal to 1 you have to take, and that sigma equal to 1, and the size of the filter. Size means here the size is 4 by 4. No, I have drawn a 4 by 4 size, but for every sigma this 4 by 4 will be different. So the equation given in the lectures is 6 sigma plus 1 you have to take as a size, because here it will be 3 sigma, here it will be 3 sigma, so approximately you can take a 6 sigma plus 1. So so take a sigma equal to 1 and take a size of 6 sigma plus 1. Then you have to pass that sigma and size to the Gaussian kernel function to get the Gaussian kernel. Then in the second function is si blur. So that is the function used for blurring the image. So there we have to pass image and sigma and size. Okay. So the steps are: first read the image manual. Then from given sigmas find kernel size using 6 sigma plus 1. Then pass the kernel size and image and sigma to si blur. Inside this si blur, you will have to call a Gaussian kernel function to get the kernel, and using that kernel you have to blur the input image using what convolved 2D function is already imported in the code. Okay, so that's all about this assignment. So it is a very easy assignment. You have to just do what just do these steps, that's all, because convolved 2D is already given. If it is not given, you will have to do this multiplication, addition and all. It is already given, so you have to just pass these values, and that's all. Okay, so that's all about this today's presentation. So do you have any questions?
Um, can you hear me?
Hello.
Yeah.
Okay.
Am I audible? Can you please explain that depth of field one more time?
Okay, so depth of field, last class did you attend?
No, no, I haven't.
Oh, okay, okay. So depth of field means what? Okay, so depth of field is if you, okay, okay. So I'll share my screen once. So, so can you see?
Yeah.
Okay, so depth of field is, so in some of the images, some portion will be looking focused, other portions will be looking blurred. So the distance at the 3D world is what is known as depth of field. So inside that depth of field you will see a similar blur. Okay, so here you can see a similar blur, no? So in some of the cameras most of the world points will be focused. So we can say that a depth of field is very large. So in this figure, so the first portion will have a similar blur, so we can say the depth of field is less. But in the second picture, from this point to the third block, it is focused, no? So we can say that depth of field is more here. In the third picture all the blocks are actually focused, but ideally speaking only one point will be focused, but we can say that they all having a similar focus measure. So that is what is known as depth of field. Okay, so in the third picture we have higher depth of field, and the depth of field depends on different factors. If we are, that depends on focal length. So that all I explained the last last presentation. So here, if the focal so if the distance of the object is more, the depth of field will be high. So you can refer uh, any material from internet also. So it is very much explained in the some of the websites.
Okay.
Okay.
Thank you. Got it.
Okay, 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 bye. Okay, thank you.